information regarding getting feedback to the team, so that'd be greatly appreciated, or feel free to try to tag up with them one by one. Team 1, are we ready to go?
Just had to find my mute button. It moved when I
There we go.
it.
All right. Floor is yours. We'll try to keep this moving as we go.
Okay. Hello and welcome to Team 1 Halo Critical Design and Production Readiness Review. My name is James Davey from the University of Washington, and I will be your host. First section, we're going to review our mission, the search and rescue for our drone. Our goal here.
I don't think whoever was responsible.
Who is talking? Thank you. Our mission is to provide an aerial platform to perform search operations for search and rescue. Our Halo drone will provide additional eyes in the sky, be more affordable and deployable, require fewer operators, and need less maintenance than traditional helicopters. Our stakeholders, our primary customer, Utah County Sheriff Search and Rescue. We are in contact with Brian Hill, who's the former president of Utah County Sheriff's R. But other potential customers are search and rescue teams across the United States and the U.S. military and the Coast Guard. In the design overview section, we will review our full assembly, the wing assembly, the empennage assembly, and the fuselage assembly. Go over our manufacturing and testing plans for these sections. To start, our full assembly, we will assemble this at the Brigham Young University when all is said and done. We have a wingspan of 8 feet, or 96 inches, and a length of 6.31 feet, or 75.74 inches. And all dimensions that you see on these diagrams are in inches. The wing is a NACA 4412 airfoil, 16-inch chords, 96-inch span. The aerodynamics of the leading edge are preserved with a 3-piece wing skin design, which you will see in more detail when we cover the empennage section. We have a wing mount that secures the 2-piece wing to the fuselage. We are manufacturing carbon fiber wing skins at EVCC that will be adhered to a foam core, and then the foam core will be protected with wing caps. And the foam core will be adhered with glue. We do have some feature analysis to do. We only finished our model just a couple days ago. We will be doing computational fluid dynamics to confirm the aerodynamics and finite element analysis for ultimate loading and for control surface interfaces. The empennage will be assembled at the University of Washington. So our stabilizers, all 3 of them have the same rough dimensions. They are a NACA 0012 airfoil. If you see down on the right-hand diagram, the leading edge is a separate piece from the top and bottom wing skins with some small overlap that will be adhered to so that we can preserve the aerodynamics. Foam core for strength with a single spar. For manufacturing, molds are shared between the vertical and horizontal stabilizers, so that reduces the number of molds that we need to produce. They will be secured to the tail boom using wing caps and a pin system to allow us to quickly make changes. If we need to repair a piece, we can just pull it off. But it should be able to securely hold everything in place in flight. Our manufacturing plan is carbon fiber again for the wing skins that will be manufactured at EVCC with the foam core and the wing caps at the University of Washington. The wing caps are going to be 3D printed. The foam core and the wing skins, again, glued together. And we do have some analysis and simulation to do here with computational fluid dynamics to confirm our aerodynamics, and FEA for ultimate loading and control surfaces. The wing cap and connector piece, as I mentioned, they are secured by pins to ease repair. And the wing caps secure the structure to the connector piece, and the connector piece is secured to the spars, to the tail boom by the spars. The spars are going to run through the tail boom, which will lock translational and rotational movement. The wing skin of the stabilizers will slip over the outset of the inserts that will constrain rotation of the wing pieces. We are 3D printing these at the UW using Onyx, which is a carbon fiber and nylon composite. And after printing is completed, we will be reaming the holes and to ensure their concentricity. These parts, we have future FEA analysis that is planned to be completed by January 12th for the shear loads from on the pins and general loads from the loading wings, and also to analyze the load transfer from the tail structure as a whole through to the tail boom.
Good morning. My name is Matthew Jones from BYU. I'll continue our discussion on the design overview. This is our fuselage. It will consist of an internal load-bearing structure and an external shell for aerodynamic purposes. We're going to show in this portion of the presentation how other parts of our aircraft will index to the fuselage. The internal structure has gone through several revisions. We have worked very closely with Everett Community College to just get feedback on our design and make sure that what we're doing is manufacturable and that is good practice for what they're doing over there. Our first version was very boxy. It was a panel structure and it was over-engineered and overcomplicated. We moved in version 2 after receiving a lot of good and prompt feedback to more of a rib, runner, and panel structure. We rounded the corners for ease of manufacturability and ease of indexing of the skin, and this greatly reduced the weight. We are still going to do an FEA analysis on this portion of the fuselage to make sure that we can handle all of the expected loads. Some of the key elements inside the fuselage for indexing are obviously, it will be a load-bearing structure. It will be manufactured from carbon fiber plates. It's an open structure, so there will be access on both sides to the electronics and the internals. On the bottom right, you can see a shaft collar that we will manufacture to index the tail boom to the fuselage. This will transfer the loads and hold everything in place. So the carbon fiber panels will be water jet cut at EVCC, and the shaft collar will be machined aluminum, also at EVCC. We were doing, as I mentioned, a load analysis on the frame, but we'll also do an FEA load analysis on the shaft collar to make sure we can hold the boom in place and it can handle the required loads. The wing and motor brackets, they will both be out of machined aluminum. The wing bracket will allow for adjustable wing mounting just to make sure that the balance of our aircraft is correct. And the motor bracket will be fixed on top of the fuselage. We will do a future FEA analysis on the motor bracket to ensure that the thrust forces are handled well by the bracket. And these will both be machined, CNC machined at EVCC. Now the shell is a 3-piece design, 2 mirrored fuselage cells, and 1 nose shell. The nice thing about this is we'll only use 2 molds for this process. There will be fiberglass layups performed at EVCC. And we still need to do a CFD analysis to determine the drag on this shell shape. The deployable payload is a 3D printed we will do at BYU. It's going to be released via servo from the bottom of the fuselage. Since it will be 3D printed, we have the option to prototype and iterate here at BYU to make sure that the design is fully ready for our final flight. I'll now go over the electronics, the components, and the connections of our system. On the left, you can see the camera system wire diagram, the way that we will connect our camera, the Micro Eagle, to the various antennae, the receiver. On the right, you'll see the avionics diagram, where we have our battery connected to our Pixhawk 4. Main components include the motor, the GPS, and other peripherals. For our power requirements, we decided that our motor was going to be the main culprit of power usage. We estimated our power using that equation. Essentially, we assumed that the motor draws 25 amps during cruise, and we assumed a flight time of 1 hour. The auxiliary components were given a very conservative estimation of 5 amps continuous draw. And with those estimations, we decided we need a minimum required power of 30 amp hours. This is an initial component layout with all of our internals, our various cameras, and their locations. We understand that this might not be the final location of all of our components, namely the battery. We plan to have the internals on a Velcro track, adjustable, so at the time of flight we can adjust our center of gravity and be able to balance our aircraft as necessary. And again, we will have access panels to do all of this. I'll now go through our systems validation, some of the simulations, prototypes, and the tests that we've performed to this point. Our initial glider test did not go exactly as planned. We had an unplanned contact with the cement wall. You can see on the right our glider design, the foam cut wings and a corrugated plastic fuselage. Now, we've conducted 7 test flights, 6 of which ended in crashes, much like the one that you saw. But we saw a consistent failure pattern in that the glider was diving left. We made a lot of adjustments in between our flights, including adding winglets for stability, and mainly, we used the lessons we learned from the August kickoff with the Bronco Flyer. We knew that making trim and balance adjustments, however slight, can have big impacts on the performance of your aircraft. And so that's led to a short, successful glide with a good glide slope and less of a dive to the left. But we wanted to do further investigation onto what was the underlying problem. We looked into our tail, which was analyzed in AVL, and we realized we'd actually misread our dimensions. Our glider was manufactured at half the necessary tail span, and so we look forward to doing our next glide test with the proper tail span. It will be double the size of what you see there, and we hope for a very successful glide test compared to what we've seen. Our finite element analysis was done on certain of our components, namely tail boom and the wing loading. These are the load paths that we use to analyze those. The wing mount bracket was the element of interest with the wing loading. We used both a positive and a negative load with different load factors obtained from our VN diagram. These produce very low max equivalent stresses in relation to our material strength, which will be an aluminum alloy machine. So we determined this bracket is a very suitable solution for transferring loads from our wing to our fuselage. Our tail boom loading was similarly analyzed with a positive and a negative load. We looked at max equivalent stress in the bar, as well as the max deflection, trying to size our tail boom correctly. The tensile strength of carbon fiber that we'll use is close to 300,000 psi. And so with a 0.96-inch diameter tail boom, and that's with about a 1/16 wall thickness, we have a successful flight with a factor of safety of 4.1. So we will also examine the stresses in the horizontal tail to make sure we can handle all the loads. But for now, we feel that we have a good diameter tail boom. We might be able to go smaller with further analysis.
Hello, I'm Tourist Moore from Tuskegee University. We purchased a model aircraft called a Bistler to test the electronics of the autonomous flight system before actually trying them on our finished airplane. Here you see the picture of the Bistler along with this electronics inside of it. The model aircraft will be used to validate a lot of the electrical components and to learn some of the bugs with the software. Also, any best practices that we should do when putting it on the UAV. So far, we have hooked up and connected the autonomous flight control system to the Bistler and connected it up to the transmitter. However, we are still waiting to receive the radio. In addition, the testing will be done at the University of Washington with their autonomous flight systems laboratory, since the FAA requires someone with a remote pilot's license to operate the model aircraft, and also because of safety concerns. So we must go when they go, and once we eventually receive the radio, the Bistler will be used to test the flight dynamics and its stability and control in flight. We will go out there and perform a takeoff and make a few laps, and then we will return. From this, we will be able to analyze and record aircraft like the center of gravity, the trim values for the control surfaces. With the Bistler, we'll also be able to prove that the Pixar controller can model aircraft from point A to point B, and we will conduct an autonomous flight path to accomplish these things. From this, we will figure out if the aircraft can fly from point A to point B, as I said, and transition from manual to autonomous flight. Earlier this week, this week and last weekend, we set up the wired the camera system and tested it to make sure we could transmit live footage from the camera to the receiver to an actual monitor on the same channel and band. In these pictures, you see the wiring layout of the camera system. So as right now, we have made sure the camera system functions properly. In addition, we tested to see if it could send signals through walls, which it can, and we tested at a range of 50 feet since we were in a confined room in the building. For future tests, we will utilize the goat farm at Tuskegee University, since it's a pretty flat straight line distance of about 2 miles. Testing location and ranges are shown in the picture right there, and we will test the transmission range, the penetration, and camera blur at running and car speeds. For our motor testing plan, we want to determine the highest thrust and the most efficient prop in terms of size and the angle of attack of the prop. Also, we want to find out the performance differences in static versus dynamic testing. At Tuskegee, we will utilize the thrust stand to vary the props across all RPMs and measure the thrust. Also at Tuskegee, we will test the motor and prop assembly at cruise speed in the wind tunnel. And after these tests, we'll be able to figure out the actual versus predicted thrust at cruise speed and the prop thrust and efficiency at cruise speed. As of right now, though, we have received the motor, even though it took a couple weeks to find it due to shipping mishandling at Tuskegee University. As you see, the motor in the top picture is different from our actual motor picture below it. This is because we are waiting for a battery and ESC to arrive at Tuskegee to carry out testing on our motor. We could have attempted to test our motor with the ESC and battery that we have from a project from DBF last year, but after talking with faculty, Dr. J. Kahn and Dr. Sunday and Mr. Heath, we concluded that we could damage our motor and or the ESC because our motor is larger than what our ESC here at Tuskegee can handle. Instead, we tested our equipment to make sure that it functions correctly, and also we ran some static tests on the previous year's motor to verify our testing methods. For our project review, I will update you on the schedule, budget, and plan testing. From taking a look at our Gantt chart, you can see that we are a bit behind due to shipping errors on the motor and radio. We received the wrong radio components twice, which is delaying the flying of the Bistler, the model aircraft. Also, we still need to polish some of our 3D drawings for future FEA and CFD analysis, as you can see by the 20% completion in that area. Overall, I think we are making good progress, and we see the things we need to focus on more now and from here forward and after the break. In January, we plan to run some full-scale CFD models of lift and drag coefficients. For our budget update, we will, yeah, that's not my fault. For our budget update, we have spent so far $8,006, and for budgeted and unallocated, we are roughly a total of 3,000. We estimate that our drone will come out to a close to $1,700. In the table to the left, you can see the list of prices for some of the various drone components inside our aircraft. All right. So in January, we plan to run some full-scale CFD models of lift and drag coefficients. Also, we run some full-scale FEA models of wing loading and load transferring to the fuselage, boom to the fuselage interface, and lift and drag in cruise conditions. So for some real-world testing that we'll be doing will be done from January to March, and we will test the autonomous system, point-to-point control flying, and wing loading under 1.5 times cruise conditions. And that is our planned testing for the oncoming months next semester. Are there any questions, comments, concerns?
We have maybe time for like one or two questions from Bo, and if not, we need to keep moving on and try to recover a little bit. Yeah.
Hey, Branko here. So if you go to the slide where you see where you show the chef collar, it's the attachment of the tail boom to the fuselage. Next one. Further down. Next. Nope. Yeah, right, that one. Okay. So I don't know if this is the final design, but if you look at your tail boom stops in between two frames, that's a typical example of disconnected load path. You may want to continue that shaft and have an attachment to the second frame, so you can react your moments with a force couple rather than relying on a clamp up at the off bolt.
That's a great suggestion. We'll take a look at extending that boom, or possibly using the panel behind it to have extra place to secure it. Thank you.
Also, when you look at your attachment between the wing and the central rim, this is really efficient in taking vertical shear. However, you may want to consider either a very good clamp up sandwiching this rib between two wings for transferring your moments around the x-axis, we call it MX, or maybe have bolts that are attaching the wing to that horizontal piece of the flange, because your roll cannot be taken so easy with the two joiners coming through those two holes there. As I said, it's good in taking vertical shear, but for your maneuvering around your axis, you may want to consider some form of attachment of the wings to that horizontal line. That's all I have.
Thank you. We appreciate that. We'll do some further analysis on that rolling moment.
All right, let's get thanks for Team 1. Next we have Team 3. If you guys are ready to roll. If not.
Yes, I believe we are. I think we're waiting on Tuskegee to our side.
Okay.
I'm waiting on host so I can share screen.
You should be able to share it as is.